Hello, my name is Matthew Wassell, and I covered HTTP latency.
Hi, I'm Elliot Chen, and I cover DNS latency.
I'm Justin Baldwin, and I covered TCP idle time.
Hello and welcome to our assignment. For this assignment, we downloaded a European Union press release from europa.eu, which is hosted on a server in Luxembourg. The file that we downloaded is 205,143 bytes, and we all tested this file on the campus Wi-Fi. For the HTTP tests, I used Google Chrome version 49.0.2623.112m and Wireshark version 2. The latency was determined by the time between the HTTP GET request that my computer sent and the HTTP 200 OK response that the server sent back. In order to test this to the greatest accuracy, I did multiple repeated file downloads and then took the average latency between them. I found that my computer sent packets with a header stating that the server should use HTTP version 1.1, and because of that, it also showed that a persistent connection should be used, as is default in HTTP 1.1. The header also showed that my computer can do gzip, deflate, and SDCH encoding. This slide shows my actual results. On the first attempt, I got 0.64 seconds as a round-trip time between the HTTP GET request and the HTTP 200 OK response. For attempt 2, I got 0.37, attempt 3 was 0.48, and attempt 4 was 0.14. The average of all of these was 0.41. As you can see, there is some variability between the attempts. I think that this error is most likely attributed to a variable load on the server.
I will now continue with the DNS methodology. So the first thing I did was clear the cache on my host system and on my browser. This allowed me, for when I first tested the DNS latency, to figure out the total elapsed time without a map path to the file. This is important because I had already visited the file once when my team and I were trying to figure out which file we were going to use for this project. Had I not removed the cache on my host system as well as on my browser, it would not have given me a reasonable DNS latency because it would already had saved the IP address and would already know where the file could be found. So after I figured out the DNS latency without the map path to the file, I then tested the DNS latency with the IP address to the file cached in my browser. So the DNS latency for the total time lapse with the IP address not cached was 0.1804 seconds. And from this, based off our lecture notes and from the book, all the following tests that I performed should have a faster time now that because the IP address should be cached within the browser, which means that when my browser tries to go to the file, it already knows to where it should go to find the IP address to get to the file. So as you can see, for test 1, it was 5.18 milliseconds. Test 2 was 0.140515 seconds. Test 3 was 0.135623 seconds. Test 4 was 0.194132 seconds, and test 5 was 0.095018 seconds. So you probably are wondering now, why was test 4 longer if the IP address was cached? Well, there's a few possible reasons why that could have been. It could be when I was sending the DNS requests to the local DNS server here at UNC, there was an increased amount of traffic here on campus with students suddenly just searching random stuff. It could have also been because when the Europa server over in Luxembourg was sending back the request, it had an increased traffic. So my request, when it was sending back the data to me, it was being queried in its system before it could be sent, and that could explain the increased time. So what did Wireshark tell us about DNS? Well, the first thing it told me was that the local DNS server here on campus took the responsibility to map the IP address to the file. And what this means is that it has both the properties of iterative and recursive queries. So the property for the iterative query is when the host sends the request to the local DNS server, and when the local DNS server takes the responsibility. The recursive property is when the local DNS server sends a request to the root DNS, and then it receives the information back from the root DNS server. And it still maintains the responsibility to map the path to the file that we're downloading. So that's how it has both the iterative and recursive properties. I also deduce this from the fact that the local DNS server always returns an answer to the host from the information that Wireshark provided to me. And I determined this because I always received the same IP address that was given to me for the local DNS server here on campus. So what I received from the local DNS server here on campus was, we got 6 answers, resource records that were type A and had the IP address values that told our host where the file was over in Europa. The next things we received were 9 authority resource records, which were type NS, and the values for those were domain names that told us where we could find the answer resource record, so we would know where the file would be. The last bit of information that we received from Wireshark was the 9 additional resource records, and all this had were additional IP addresses that the Europa.eu server could be reached at.
For the TCP section, we calculated the latency, or the TCP idle time, using formulas from the TCP performance slide set, which was slide set 13, using the formula on page 8 and the formulas on page 9. We found our value for R from a website called speedtest.net, which gave us an R value of 38.21 megabits per second. This is the main value that could possibly have changed depending on the amount of traffic on the wire at one time. And it's possible that over more repetitions, our R value could have changed, which would slightly change our latency time. But for this experiment we did an R value of 38.21 megabits per second. Our round trip time and our S were both given in the Wireshark data. Round trip time was calculated using an average of the round trip time of multiple packets, and S was the average segment size for the packets given from the Wireshark data. Our O value is the size of the file, which is approximately 205 kilobytes, and we calculated K and Q, using those values, and then from there could calculate P by finding the minimum of those two values. We finally calculated the overall latency of TCP using the formula from the slide set: 2 times the round trip time plus O over R plus P times the quantity S over R plus RTT minus the quantity 2 raised to the P minus 1 times S over R. After calculating everything out, we found that the overall latency of TCP under a slow start is equal to approximately 0.2468 seconds. On the right side of the screen, you can see a map of the amount of sequence numbers over time. You can see the slow start, where at a little bit before 0.3 seconds, only a few packets are sent, and then as time goes on, gradually more and more packets are sent with higher sequence numbers. Once again, the TCP latency was calculated using the equation on slide 8 of slide set 13 and the formulas on slide 9 of that same slide set, the TCP performance slides. Latency was calculated again to be about 0.2468 seconds. Possible sources of error was we got a reset flag halfway through the TCP transmission where the server was overloaded and they had to switch IP addresses in order to continue the rest of the transmission. So it's possible that at that time the European Commission server had too many people trying to accept the connection at one time, and we had to transfer. So it's possible that the TCP time actually took slightly longer than it normally would. Increased number of repetitions could also improve consistency in this calculation. Going back to what I was saying earlier, the value for R was calculated just once by using speedtest.net, but it's very possible that at different times of the day, that value for R could be greater or smaller, depending on the amount of people on the network at one time. From additional analysis, we see that there was packet loss detected occasionally, about 4 or 5 times during the TCP transmission, but the server resent the lost packet typically in under 1 millisecond. There was only one instance where they resent a packet and it took longer than 1 millisecond. After continued duplicate packets and out of order packets, the server eventually sent a reset ACK, which told the client, which told my computer, to move to a different IP address to talk there to continue the rest of the transmission. After that reset ACK, there was no more packet loss and there was no more duplicate ACKs, and the rest of the file transmitted successfully.